Okay, so we are good to go. So what we're going to be doing today is we are going to introduce our final hypothesis test. So there is one more hypothesis test you're going to learn in this intro to statistics, and that is the analysis of variance, which is the final major test that people in psychology often use. And you'll see exactly why we needed this one today. We'll take a look at the logic behind it, how it's different from a t-test, and that will round out your introduction to statistics experience. However, before we get to that, we are going to do the Exam 3 in-class take-up. So if you haven't already, go to Canvas. You can open your graded exam to follow along. We are going to do this about as quickly as possible. So make sure that you have it open so you can follow along. And I will fire up my SPSS as well so we can do this live. And for anybody watching this on YouTube, this is where your experience ends for right now, and we will come back after the exam has been taken up. All right, so there we go. So that was the exam number 3 take-up. So before we leave exam number 3, just kind of give you a sort of State of the Union address type thing here. One of the great things about stats is it's very clear to track kind of student progress. So we've seen these before. We've taken a look at the histograms for the distribution of exam grades. So once again, we have exam grades on the bottom axis here. We have frequency on the y-axis here. So the higher the bar, the more students that got each particular score. And you can see that at the beginning of the semester, scores were pretty much spread out across a wide range. And as I mentioned, it occurs at different times for different students, but if you follow the program, if you do the work, you will finally have, make sense, it'll come to you. And it's very gratifying when you see exam 1 to exam 2. You can see that shift towards more understanding, towards those higher and higher exam scores. And if you take a look at exam 2 compared to exam 3, you can see that basically almost everybody is now at that stage where most of it is making sense. We still have a couple of students that seem to be struggling. Hopefully you can turn it around in the final exam. We do have that sliding scale of forgiveness, so remember that as well. But do make sure that you are doing what you need to do for exam number 4. So it's still going to be SPSS. It's going to be half on confidence intervals and half on ANOVAs. So the confidence intervals, as you know, are basically one step beyond t-tests. So you need to know how to do a t-test in order to do a confidence interval. So make sure that you're rock solid on t-tests. Most of you are. Okay, so make sure that you know where you lost your points, in this take up here. Look over your exam on your own. Make sure that you understand what was the issues. And then make sure that you get your confidence intervals on point. And if you are struggling with SPSS, is what I'm assuming the issue is here, make sure you do something about that. Come by an office hour, watch some online videos, go back and rewatch the lectures on the YouTube channel. Do what you need to do because we got one last big chance to improve your grade. And remember, the better you do on an exam, the more it's worth towards your final grade. So you really have a chance to turn it around substantially by doing well on this final exam. All right, so that's the end of the in-class take-up. So now let's go into ANOVAs. And what we're going to do today is we're going to take a look at the logic of ANOVAs. Why do we need ANOVAs? What are they for? What is this new hypothesis test deal all about? So we're going to start it up with, we're going to switch gears. We've been talking about human psychology for most of this course. Now we're going to talk about animal psychology. We're going to talk about comparative psychology, is another name it's known by. And we're going to take a look at a study on understanding the behavior of animals. And the question that this study wanted to address was the bizarre behavior of migration. So if you know things about birds, probably one of the things you're aware of is that many birds migrate south for the winter. So the key aspect, though, is that many of them do, but many of them don't. So here's a kind of a plot of the migration paths for many birds. And as you can see, some of them are, they're pretty long, some of them are a little bit short, but some of them are just massively long. So this is the longest migration path for any species of bird, all the way from the northern hemisphere, all the way back down to the southern hemisphere, and that's for the Arctic tern. And literally, these are death-defying, physically exhausting, almost near-death experiences for these birds. So why would they do that type of a behavior? Why would they put themselves at such a risk to go through migration when other birds are quite capable of surviving winter in a winter climate? So what is the difference between blue jays and cardinals who can stay in a winter climate? What is the difference between the birds that don't migrate and the birds that do migrate? What causes this migratory behavior? So there was a very interesting study that came out. It should be available in Canvas if you're interested in checking it out. But they hypothesized that what is the causal factor is the intelligence of these birds. So the term bird brain is exactly what they were looking at. So they hypothesized that more intelligent birds with higher cognitive abilities, they're the ones that are able to learn and implement strategies to survive in the winter. So birds, for example, have astounding memories. Some birds have phenomenal memories where they can hide things in 1,000 locations and remember each one of those locations. It's phenomenal, some of the work that's been done on bird memory. So could it be that birds that do not migrate are just smarter? They're just more intelligent. They're more able to find food. They're more able to store food and remember where it was than birds that do migrate, which might be less intelligent. So this was the question that they asked, and what they did was they measured the actual sizes, the relative sizes of the bird brains. So basically, how big is the brain compared to the rest of the bird, and saw if birds with bigger brains migrated less than birds with smaller brains. So that's what they were looking at. It's a hypothesis test. However, we're going to see that they could not answer their question using a t-test, and we're going to see why when we look at ANOVAs. So we're going to introduce the idea of ANOVAs. We are going to take a look at the logic for the analysis of variance, and then that's going to be the end of today's class. We're going to see the need for ANOVAs, and then we're going to see what they're all about. And then next class, we're going to learn how to do ANOVAs in SPSS. All right, so ANOVAs. Up until now, ANOVAs were not required. We didn't need them. Because up until now, we were interested in the difference between two populations. So if you take a look at exam 3, every question was about two populations. Were the scores bigger after supplementation than before supplementation? Were instruction set 1 different from instruction set number 2? Were optimism scores higher this year than they were last year? It's always been a comparison between two populations. And what we've done is we've taken a sample basically from one population, we've taken a sample from another population, and we've done a t-test to see if the differences in these samples indicate that there's a difference between these two populations. Well, that's great for some questions, but oftentimes you want a little bit more of a complicated question, or you need to ask a bit more of a complicated question, especially in humans, where we are not oftentimes just the difference between one or two options. Sometimes there's even a third option. So what do you do if you want to test not between two populations, but you want to test between three populations? And you have a sample from that third population. How do you analyze this experiment? How do you do this particular hypothesis test? So if you introduce population 3 here, and let's just reorganize those. So we got population 1, 2, 3. How is it that you can analyze this particular data? So we have the data from our samples. What is it that we can do? Well, first off, we'll talk about what we cannot do. what we're not allowed to do. And what we're not allowed to do is multiple t-tests. So ANOVAs exist because you cannot do multiple t-tests. And what you might have considered and what other people did prior to the ANOVA, what they did incorrectly, is you might say to yourself, all right, we got 3 samples here. So why don't we do this? Why don't we just do a t-test between sample 1 and sample 2? And that'll tell us if population 1 is different from population 2. And then we can do a t-test between sample 2 and sample 3. And that'll let us know if population 2 is different from population 3. And then the only question left is population 1 different from population 3? And we can do a t-test between sample 1 and sample 3. Problem solved, we're all done. Hypothesis testing, wins the day. Unfortunately, you can't do that. That is not allowed because that has a problem. That is known as multiple comparisons. We're making 3 comparisons, and making those 3 comparisons in a single experiment is not allowed, not with a t-test. So you'll notice that up until now, we've only ever made 1 comparison, right? Terry cloth versus wire mesh mothers. 5-second versus 10-second timeout. You just needed the 1 comparison. So this issue hasn't come up yet, but what exactly is the issue? Why is this a problem? And the problem is because it inflates that experiment-wise alpha rate. It inflates that all-important, keep your hands off of it, do not touch. It inflates that alpha rate. And that is something that we cannot allow to happen. So what do we mean by experiment-wise alpha level? Well, we'll contrast it with the test-wise alpha level. The test-wise alpha level is the alpha level for each test. The experiment-wise alpha level is the alpha level for the entire experiment. And these 2, test-wise and experiment-wise alpha levels, have been the same in the t-test because the t-test just does 1 test. So the test-wise and the experiment-wise alpha level are the same. But the test-wise alpha level, that's the alpha level that you use for each comparison that you make. So if you do this t-test, what's the alpha level that you choose? If you do this t-test, what's the alpha level that you choose? This t-test, what's the alpha level that you choose? It's the alpha level for each test. That is your type 1 error. That is your chance of saying there is an effect when in fact there is no effect. That's your chance of having that false positive, that's saying that yes, these are different, when in reality the populations are not different. And that's always a probability, and that's a mistake, and that's why alpha levels are typically set low, right? So when you say my alpha level is 0.05, what you're saying is that I'm willing to take a 5% chance that I'm going to find an effect when in reality there is no effect. I'm going to find a difference when in reality there is no difference. So we choose that very carefully, right? In psychology we use 0.05, 5%. In medical studies they might use 0.01, 0.0001, 1% or a tenth of a percent, depending upon how bad that error would be. But whatever it is, you want to control it. What happens is if you do multiple comparisons using an alpha level, your experiment-wise alpha level goes through the roof. And you have this accumulated alpha level that skyrockets and basically increases the chances that you're going to find something when nothing is actually there. And this is an accumulative type 1 error. So to illustrate why this is the case, let's take a look at a test-wise alpha level of 0.5. Right? So literally a test-wise alpha level of 50%. This would be, for example, if your statistical package was flipping a coin. So if you flip a coin, you got a 50% chance of saying an effect is there when there is no effect. Right? If there is nothing going on in your experiment and you flip a coin and it comes up heads and you say, I'm going to reject the null hypothesis, it means you have a 50-50 chance of getting it right or getting it wrong. We have an error, a test-wise alpha level of 0.5. So we'll use this for an example because the math on it is easy to illustrate. So let's suppose that there is no effect, right? We have these 3 populations. There's no difference between any of the populations. There's no effect whatsoever. What's the probability that you're going to make one type 1 error after one comparison? Right? What's the probability that you're going to flip that coin, and even though there's no effect, that coin is going to tell you, yes, there is an effect. It came up heads, yes, there is an effect. Well, when we set it up like that for that first test, we got a 50-50 chance of being wrong. All right, so let's say that it's tails. When tails comes up, it's incorrect. Tails is when we say that there is an effect. So if we do one test, we got a 50-50 chance of saying, yes, there's an effect, when in fact, there is no effect. So the probability of making that type 1 error is 50%. But that's fine, because that's exactly what we wanted. Right? We said, all right, we'll use an alpha level of 50%, and the probability that we'll make a mistake is 50%. That's exactly the correct kind of situation to be in. However, that's only after one test. What happens when you do 2 tests? Well, if you do 2 tests and you flip the coin again, and once again you got a 50-50 chance of being wrong. But this is now your second test. And the probability that you'll be wrong at least once, you can be wrong on the first test, you can be wrong on the second test, or you can be wrong on both the first and the second test. There's only a 25% chance that you'll be correct on both tests. So that alpha level that we want to be 50% has now ballooned to 75%. That's no good. And then, if we do, that's only 2 tests. If we do 3 tests, then once again, we have the probability 50-50 of getting a tail on that third test. So the probability of getting heads on all 3 is about, what, 12 and a half? Yeah, there it is. So the probability of making an error and saying that at least one of these is different when none of them are different is 87.5%. That's an issue because we want our alpha level to be 0.5. We want it to be 50%, and all of a sudden our real alpha level has ballooned up to 87.5. Any questions on that so far? All right, so that's for a weird alpha level of 0.5. What about a real one? What about an alpha level of 0.05? So let's say we're flipping a really, really unfair coin, where it comes up heads 95% of the time, it comes up tails only 5% of the time. Once again, let's suppose that there's no effect. No effect whatsoever. What's the probability that you're going to make at least one type 1 error? Say that there is an effect, when in reality there is no effect after one test. Well, we flip this really unfair coin. 5% chance that it'll come up tails, 5% chance that we're going to make that type 1 error. That percentage is 5%. And once again, this is fine. We're willing to risk at a level of 5%, and our level of risk is 5%. That's exactly where we want to be. But what happens after 2 tests? When you have a 5% chance of making an error on the first test, and a 5% chance of making an error on the second test, the chance that you'll make an error on one of those tests almost doubles to 9.75%. And after 3 tests, it almost triples, all the way up to 14.3%. So we want an alpha level of 0.05. We only want to take a 5% risk. But because we've done multiple comparisons, we are now up to a 14% risk, and our type 1 error has inflated. So these are kind of hypothetical examples. I mentioned to you before that people have done this error previously, and one example of that is this study right here, which was an analysis of the Minnesota Multiphasic Personality Inventory profiles of 40 college-educated overt male homosexuals. So this was one of the first studies that was done on the personalities, the behaviors of homosexual individuals. And what they found was that there were personality differences, that homosexual males were significantly different from heterosexual males on certain personality types. So the way that the Minnesota Multiphasic Personality Inventory works is that there are a number of scales. It looks like about 12 scales there. And they tested them on each of these. And what they found was that there was a significant difference in psychopathic deviant and masculinity, femininity, and there was also differences in schizophrenia and hypomania. So homosexuals, I believe, scored higher on schizophrenia, they scored higher on hypomania, they scored higher on psychopathic deviant, and they scored differently on that masculinity, femininity scale. The issue with this is that they used t-tests. For each of these scales, they used a t-test, which means that they were making multiple comparisons. Instead of just one comparison with one experiment-wise alpha level at 0.05, each comparison inflated the probability that they would find a difference when there actually wasn't a difference there. And that's exactly what happened. They ended up finding differences, significant differences, when they weren't there. They ended up making type 1 errors in their study. And again, they did that because of these multiple comparisons. So this type of a study is a psychologically relevant study. We want to know these things. We're interested in behavior. We're interested in cognition. But we need a way of making those multiple comparisons without inflating that type 1 error rate. What we need is a method to make those multiple tests without messing up our alpha level, and that's what an ANOVA does. So now we know why we need an ANOVA. Any questions on that before we go to the kind of nuts and bolts of an ANOVA? All right. So now we know we need an ANOVA, and this is one test. It's got one alpha, and it'll evaluate your mean differences without inflating your type 1 error rate because it's one test. All right. So before we get into this, there's a number of different ANOVAs. We are going to end this class with the simplest one. All right. So this is going to be not just your introduction to statistics. This is also your introduction to ANOVAs. Right. So there are, just the way there is multiple t-tests, there are multiple different ANOVAs. But we're going to start off with the simplest one. So just to kind of illustrate some of the ideas that determine what type of ANOVA you're dealing with, there's the idea of a factor. And a factor is your independent or quasi-independent variable. A factor is basically your variable of interest. What do you think is causing the behavior? So for example, type of mother would have been a factor. And then you have the other idea of levels. And levels are the individual conditions that are in that factor. They're the individual values that that factor can take in a particular experiment. So for example, in Harlow's monkey study, in his infant attachment study, there was one factor. That was type of mother, right? That was the only thing that they were looking at. Does the type of mother affect how long monkeys spend with the surrogate mother? And there were two levels, right? They were either a wire mesh mother or a terry cloth mother. So when you have one factor with two levels, that's a t-test. And that's why we were able to do a t-test in this situation. When we take a look at a study like this one, it goes, when people learn a new task, their performance usually improves if they are tested the next day, but only if they get at least 6 hours of sleep. The following data supports this phenomenon. The participants learned a visual discrimination task one day, and they were tested on the task the following day. Half of the participants were allowed to have at least 6 hours of sleep, and the other half were kept awake all night. So in this condition, in this experiment here, we're looking at one cause. We're looking at one factor, and that factor is amount of sleep. We're also only looking at two levels. We're looking at 6 hours of sleep or no hours of sleep. So in this case, once again, one factor, two levels, that is a t-test. All right, we'll read this one here. Strack, Martin, and Stepper reported that people rate cartoons as funnier when holding a pen in their teeth, which forced them to smile, than when holding a pen in their lips, which forced them to frown. This is called the facial feedback hypothesis of emotion. It's one of the kind of weirdest psychology theories ever out there. Has a ton of data to back it up, though. Basically, the idea is that when you experience an emotion, your body reacts in a certain way. Your mind then reads your body and interprets the emotion. So a researcher attempted to replicate the results with a sample of 16 adults between the ages of 40 and 45. For each person, the researcher recorded the difference between the rating obtained while smiling and the rating obtained while frowning. So once again, we have one factor, which is facial expression. That's the only thing. Does facial expression affect your rating of cartoons? We got two levels. We got smiling and we got frowning. So once again, this would be a t-test. All right, but notice that they studied 40 to 45-year-olds. What if you as a psychologist were interested in this effect and said, is it the same across ages? So what if you wanted to know if this worked the same for children versus young adults versus older adults? Well, then you could do a new experiment where you tested children, young adults, and older adults and had them smile, had them frown, and had them rate cartoons. And in that case, you would have two factors in your experiment. Factor A would be facial expression. Are you smiling or are you frowning? Factor B would be age. What age are you? So now there's two potential causes. And the levels for factor A, facial expression, we got two levels. We got smiling or frowning. The levels B for age, we got three levels. Children versus young adults versus old adults. Once you go beyond once you go beyond one factor to two and above, and or once any of your factors have levels 3 or more, then you're in ANOVA territory. That's when you need to do an ANOVA. So depending upon the combination and the design, we would do different types of ANOVAs, just like for t-tests. But what we're going to do for this intro to ANOVAs is we're going to consider the simplest one. It is a single factor, one independent variable, one cause, independent measures design. So different samples in different conditions. And it's going to have one factor, but it could have as many levels as you want. So it could have 3 levels, it could have 5 levels, it could have 7 levels if you want, but there's one cause with multiple levels. So if we were doing, for example, Harlow's monkey study, and we wanted to test, no, not Harlow's monkey study, if we were doing the Loftus and Palmer study, and we had one group, and we say, how fast were the cars going when they smashed into each other? And we had another group that said, how fast were the cars going when they hit each other? And then we had a third group, and we said, how fast were the cars going when they violently smashed into each other? We got 3 groups. That would be one factor, the way the question was phrased. 3 levels: hit, smashed, or violently smashed. So for this hypothesis test, it's going to work the same way. We're going to have those same 5 steps that we had before. The only, well, not the only, the big difference, one of the big differences here starts with the hypotheses. So we're still going to have a null hypothesis, and we're still going to have a research hypothesis. The null hypothesis is this here, that population 1 equals population 2 equals population 3 equals population all the way up to your final level. So the null hypothesis, and ANOVA, you can think of it as a hyped up, two-tailed t-test, right? So the hypotheses are like two-tailed hypotheses, where the null hypothesis is that every population has the same mean. The means of every single population that we're testing are the same. That's your null hypothesis. Remember that your research hypothesis has to cover every other possibility. Every other possibility, in this case, is difficult to express mathematically. Because every other possibility is that if the null hypothesis is that every population is equal, the research hypothesis is that at least one population mean is different, right? That's the complete opposite. Not that they're all different, but that at least one of them is different. So the null hypothesis, easy to write out. Everything is equal, they're all the same. The research hypothesis, difficult to write out, because it is that at least one of them is different. So if we wanted to write it out mathematically, we would have to say the mean of population 1 does not equal the mean of population 2. And or the mean of population 1 does not equal the mean of population 3. And or the mean of population 1 does not equal the mean of population 4. And or the mean of population 1 does not equal the mean of population all the way up to your final population. And then you start it all over again. And or the mean of population 2 does not equal the mean of population 3. And or, and you just keep going. And you can see that it can get out of hand. So we're not going to write it out mathematically. We're going to write it out in an English phrase. At least one population mean is different from the other. It could be that they're all different. It could be that two of them are different. But we know that at least one of them is different. All right, so we have a new hypothesis test. That means we're going to have a new test statistic. So the t-test had a t-statistic. The ANOVA has a thing that's like a t-statistic, but a little bit different. So it takes its sort of structure from the t-test here. So every single t-test that we've been doing can boil down to the difference that you actually found between your samples divided by your standard error, which is your expected difference. So every single t-test that we were doing is the difference that you found divided by the difference that you expected. That's what it all boils down to. ANOVAs do the exact same thing, except instead of differences, they analyze variances. It's right there in the name. It's the analysis of variance. So whereas a t-test was what was your expected difference, what was the actual difference divided by your expected difference, an F statistic for ANOVAs, F for ANOVA, is what is the actual variance that you found between your samples, and what was the variance that you expected to find. So again, it's that what did you actually find divided by what you expected to find. So the last thing we're going to take a look at today is what are these variances that are being analyzed? Where do they come from? And we're going to take a look at that right now. So let's say that we have this experiment here. We got one factor, 3 levels. We get samples from 3 different populations. Remember that this is an independent means ANOVA. So this sample here and the sample scores that they have, these are different people than this sample here. And these are different people than this sample over here. Right? So we have an independent means t-test. We have an ANOVA, which is an analysis of variance. But where does this variance come from? What is the variance that we're analyzing? So the first thing that we're analyzing, or the first component, is the total variance. And the total variance is the variance between all scores. So this is variance in terms of variance and standard deviation. This is variance going back to like week 2, where we were taking a look at measures of central tendency and variance and standard deviation. So your total variance is just the variance for all your scores. So you literally take all of your scores, all of the scores from each sample, and you find out what is the total variance. How much variability is there amongst all of the scores? So that's your total variance. That's the amount of variability in the entire experiment. Another component is the between treatments variance. And this is the variance among the treatments, right? This is the variance between the treatment means. What that is if you take a look at the means for sample 1, for sample 2, and for sample 3, the means for these samples are different, right? They're not all the same. There's some variability there. So between treatment variance measures the variability between treatments. It measures the variability between these different samples. So that's the next component, the difference between, or the variability between the sample means. And then the last part is called within treatments variance. And within treatments variance is the variance within each sample. So in sample number 1, you'll notice that even though they've all been treated the same, they all came from sample number 1, they all came from the same experimental condition, their numbers are different, their scores are different. There's variability there. That is within treatments variance. How much variance is there? Really? How much variance is there? Thank you. How much variance is there in that sample right there? Same thing with sample number 2. Notice their numbers are different. How much variability is there in that sample right there? And then sample number 3, numbers are different. Even though they've all been treated the same, they're individual people, right? They're going to vary on their scores, so their numbers are different as well. So that's what within treatment variance takes a look at. What is the variability in each of these samples? Basically, how different are people just in general? In each sample, if you're treated the same, how much variability do we have? And this is the three components of variability. And then a little bit of mathemagic gets us to this point, which is that your total variance, the variance in the entire experiment, actually equals your between treatment variance plus your within treatment variance. So those three components equal each other. Total variance equals between treatment, the variance for your means, plus within treatment, the variance within each sample. And this is very, very helpful. As we're going to see, this between treatment and within treatment is where ANOVAs actually are able to do the work that they do. So let's take a look at how this all goes down. By taking a look at where does this variance come from? Where does the variability come from? So we're going to start off with between treatment variance. Between treatment variance, that measures differences due to treatment effects, and it measures differences due to random variation. So when we find that there is a difference between the mean of sample 1 and the mean of sample 2, that could either be treatment effects, that population 1 is different from population 2. That could be one of the reasons that this mean is 1 and this mean is 4. But it can also contain random variation, right? So these people here are different from these people here. So maybe this difference also has an amount of random variation. We just happen to get low scoring people in this sample and higher scoring people in this sample. So it could be from the variation between people, right? People are just different. Or it could be because the treatment actually caused a difference. The populations are actually different. So the differences between the treatment means can be due to either treatment effects or just random variation, just people being different from each other. However, when you take a look at the within treatment variance, that variance only measures differences due to random variation. Because when you take a look at the variability inside each sample, there is no treatment effect here. Because sample from population 1, everybody here got treated the same. So the fact that this person scored a 0 and this person scored a 1 can only be due to random variation between those two people. The fact that this person scored a 1 and this person scored a 3, they were treated exactly the same. It can only be due to individual differences between the people. So all of these differences here that within treatment variance is measuring can only be due to random individual differences. Same thing here, random individual differences. Same thing here, random individual differences. So that is the only component of within treatment variance. And because of that, that is our door to get to treatment effects. Because what we can do is we can now calculate how much variance is there between the samples and how much variance could we have expected. Because the variance between the sample means, that is your treatment effects plus random variation, right? So the variance you'll find between the samples, that's due to treatment effects plus random variation. The variance due to expected variance, that's just random variation. And luckily, up here, we got treatments and random variation, aka between treatment effects. And luckily, here we have just random variation on its own, aka within treatment variance. So the F statistic measures how much variance do we have versus how much variance would we have expected by taking the between treatment variances and dividing it by within treatment variance. All right, so we got a few more minutes. We are going to wrap up with the final peek behind the curtain here. So what does this all mean? Well, let's take a look. So we'll break these apart just to kind of really quickly analyze them between treatment variance and within treatment variance here. Again, between treatment variance, treatment effects and random variation, within treatment variance, just random variation. So what happens to this formula? Well, let's start it off when there actually is a treatment effect. Let's start it off when there is no treatment effect. So if there's no treatment effect, that means that treatment effects equal 0, right? That's the definition of no treatment effects. What happens to your F statistic? Well, your F statistic, treatment effects plus random variation divided by random variation, becomes 0 plus random variation divided by random variation. 0 plus anything does not change that thing, so it equals random variation divided by random variation, and we know that one thing divided by itself is going to equal 1. So when there is no treatment effect, you're going to get an F statistic that is close to 1. That is the indication. That's what happens when there's no treatment effects. What about when there is a treatment effect? What about when your treatment effect exists? It's greater than 0. Well, in that case, we'll give our treatment value, our treatment effect a value of x, right? So x is just some number. It's greater than 0. And we're doing this so we can break this up into two components. So we got x divided by random variation plus random variation divided by random variation. And we know that this here equals 1. So this is going to be something. This is going to be 1. You add the two together and you get a number bigger than 1. So when there's a treatment effect, you end up with an F statistic that is bigger than 1. And much like a T statistic had a T distribution, lo and behold, your F statistic has an F distribution, and that's what it looks like. So it's still a kind of bell curve. It's a really skewed bell. It's really positively skewed in this case, but it works exactly the same. It's a distribution of F scores, and what we're going to do in our hypothesis test is we're going to pick a tail that is equal to our alpha level. We're going to end up with a cutoff score, or in this case a cutoff probability, that will put, for example, 95% of the distribution in the body, 5% of the distribution in the tail, and then that's going to be your critical region, exactly like we had it before. And then we're going to take a look at our F statistic, our statistic for our hypothesis test. And if the F statistic ends up in the body of the distribution, we are going to accept the null hypothesis, just like before. However, if that F statistic makes it into the tails, we are going to reject the null hypothesis, just like before. So it's a new situation, it's a new hypothesis test, but as you're going to see, it's exactly the same logic as before. We have a distribution, we have a test statistic, and we have different regions. If it crosses into the region, into the critical area, we reject the null hypothesis. All right, well that was a full class with that exam 3 take-up. So are there any real quick questions before we wrap it up for today? All right, so that's all that I wanted to cover for today. It's basically the end of class. So we will take a look at how to do all of this in SPSS next time. And then that'll be our second last class. And then our final class will be a review class for exam 4. Other than that, we are done for today.